I don't know. No, probably business. Repeat it.
We'll run through these really quickly again. So the first one, B3A1, what was it? It was the wavelength, which is H over P, H over MV, and all that information is given. 3.095. You have it from yesterday? Yeah, okay. So what was it? 3.095. Yeah. Okay, and then part 2 was the work function. So we had to use the formula that the energy of the light plus the work function energy equals the kinetic energy. And so the work function equals the energy minus the kinetic energy, which would be HF minus a half mv squared, which was hc over lambda minus a half mv squared. And what was that? 3.385 electron volt. Okay, that was fine. And then part 3 was the first we had to get the threshold frequency, which was the work function over H. Or H over work function over H, isn't it? Like this?
No.
Yeah. Then the wavelength is C over F. So that would be C over work function over H. So that was HC over work function. And what was that yesterday?
360
micrometer. Grand? Okay. And we had our explanation. So our explanation for why increasing the intensity does not change in the value of the maximum wavelength. So the key point was that only one electron can be freed per one photon. So if you have twice as many photons, you could have twice as many freed electrons. However, the electrons require a minimum energy, which is the work function. And the photon's energy depends only on what? Only on the frequency. Yeah. So greater intensity doesn't mean
We can ask a question.
doesn't change anything here. Yeah.
After that electron is free, where to go?
Just leaves the plate. Just moves away from the plate. That's all. It's released. Yeah. I wrote something a bit better than this yesterday, but anyways, it doesn't matter. Right. So the next part, B part 1, it was how the absorption line spectra are produced. So I think we did this yesterday. What you needed was gas, wasn't it? Yeah. And then you have the white light. And the white light, you shine it through the gas and it comes out and it goes through a prism and you get the spectra here. And we described this process. And the question, although it said how, there was also a why. So what's the reason why some of the colours are missing? So for example, here's the explanation. So a black fringe, I guess, that corresponds to a missing colour. And a missing colour means a missing wavelength, because different wavelengths have different colours. I think we said red was, what was red, like 350 nanometers, and violet was like 650. Anyway, so missing colour means missing wavelength, and missing wavelength means missing photon of that wavelength lambda, which means that missing photon of a certain frequency. Now, why would a photon of a particular frequency be missing? Well, the reason it will be missing is because that was some electron took that photon to be freed, and it required that frequency. So that would mean electron required exactly hf of energy to be freed. So the photon is missing because that photon had the right amount of energy to free a particularly trapped electron. And I think this is where we stopped yesterday. I accidentally deleted the video yesterday because my hard drive hit 100% and I couldn't actually record anymore. 500 gigabytes. Yeah, I couldn't save anything because it said hard drive full, and when I checked it was at 100%. SSD? No, I just deleted stuff. But I accidentally deleted the video from yesterday, so whatever. Okay, so now the B part. Oh, well, that is the B part. B part 2.
Yes, now
The calculations. Right, so what is the name given to n equals 1? What do we call this energy level?
first energy.
Yeah, no, true, but I think it has a special name. It's called the ground energy level. What, does he allow first energy level in the marking scheme? No.
Ground state.
Yeah. Right, so when we go from energy state 3 to energy state 1, there is some energy change. How much the energy change here from 3 to 1? There's 12.07, look, there's 12.07 electron volts lost when the electron changes from the two energy, it goes from 3 to 1. This energy is lost by emitting a photon of that energy. So, is it not 12? I'm sorry, let's see, 13.58.
Is that 13?
What?
Okay, sorry.
Dude! Whatever. Right, so you have HF equals 12.07 electron volts. HF equals 1.93 times 10 to the minus 18 joules. Hc over lambda equals 1.93 times 10 to the minus 18 joules. So we can finally get the answer here. Lambda equals 1.93 times 10 to the minus 18 over Hc. H is number 6 and C is number 20. I must have done something wrong because that number seems too big.
Why is not minus with the minus?
Huh?
Why is not the minus with?
No, it's HC4 for heat.
Do I have it upside down again?
Yes.
Ah, that explains it. This is upside down. So we need to flip it just. Sorry, yeah. Lambda is Hc over this. That's why it's so stupidly big. Right, so if I type that into the calculator, that's better. One sec. Let's go with nano. 102.7 nanometers. Yes, Fahad.
Why is it not minus with 12.07?
Wait, say that again. Why is it not what?
Minus with 12.07?
But it is minus with 12.07 because it's lost. And this energy goes into the photon. The photon has to have positive energy. No?
Think of it like this.
If you had minus, then your wavelength would be minus. So tell me what minus 1 meter of wavelength is. The wave is travelling backwards through time. So look, if I have a euro and I lose it, that's a minus €1 to me. If you pick it up, is that a minus €1 to you? No, it's a plus €1 to you. So the electron loses, it's a minus 12, but the photon gains that. So the photon is positive. Because the photon picked up the euro that the electron dropped.
If we, for example, some other question, if we get, if we like take the difference,
Yeah.
delta, so if it's minus, just remove the minus.
Oh, this is so not a thing right now we're having. The electron's energy, yes, what was the energy here? Minus 3.39, yes? And this one here, minus 13.58. And it goes from here to here. Now at the beginning, hey, look up. At the beginning, there's no photon. And at the end, when the electron moves down, there is a photon. So the energy at the start must equal the energy at the end, plus the energy of the photon. Correct? Yeah, so then the photon energy is 13.58 minus 3.39. No, HF. HF. I'm going back. Right, what's next? Determine, is that right firstly, KJ? If you can see from over there.
Yes.
What number do you see?
1.02.
Okay, fine. Okay, stop talking now. Right, next. Determine the frequency, minimum, yes indeed, to go from 1 to 4.
You just have that, just want to run that.
So how much energy, what's the frequency? Yeah, okay, so to go from 1 to 4, okay. So what's happening here? We're at energy state 1 and we want to go to energy state 4, so we need to give it some energy, of course. How much energy do we need to give it? Well, what's the difference between state 4 and state...
12.73.
Now state 4 is 0 actually, isn't it?
No.
0 energy. Or, no, sorry, minus 0.85. Minus 13.58. So it requires 12.73 electron volts, which means HF equals 12.73 E, which means they want frequency, so F is 12.73 E over H. What number is H? I mistyped it. 12.73 times E over H. So the frequency is quite a large frequency. 3.078 times 10 to the 15th hertz. Yep.
You wrote 3 as a E.
No, I didn't. That's an E.
Down.
Oh, wow, okay. Go down. From chemistry, what's ionization energy?
The energy required to remove one electron.
And if the electron is in the ground state, how much energy does it need?
13.58.
What's the answer. See what I mean? It's a good question. Still, it's 1 mark for writing down a number that's in the question.
1%.
It is, you are right, it is 1% of your final exam result. A generous 1%, if I may say so. Right, close that.